All right, number 1460. We have a problem given to us. We said the following data were collected for the reaction. All right. This is the data here, and we want to know what the rate law for the reaction is. I should note also that we have the chemical reaction M plus N yielding P plus Q. So our chemical equation here, M plus N going to P plus Q. And we are given various chemical concentrations, right? And we want to know the rate law. Well, the skeleton rate law, what I call the skeleton rate law, right, is just the rate is going to be equal to some constant K times the concentration of M raised to some exponent times the concentration of N raised to some a different exponent. Or maybe the same, or just a different variable. All right, so we see that this rate statement here, right, is made by, again, this is the rate, and the units for the rate are molar per second. It's how the concentration of the reactants here change over time in units of molar per second. K is going to have some units that right now might not be clear to you, so we'll just leave out those units for now. The units here are going to be molar to some value, molar to some value. Now it just happens to be the same variable, right? And the units here are also going to be molar to some value, right? So right now we can't tell what the units for K are until we identify what these exponents are. But we can identify the exponents by looking at two of these scenarios in which only one component changes. For example, here's our first two reactions here, and we see that we double the concentration of M, all right? And I can also see that as M is doubled, the rate doubles as well. So that means that if I double this, the rate doubles, and if you look at that equation, that would have to mean that this X is 1, right? So here below here I'll have my my rate law that I'm fixing as I learn more information about it. I'll leave out the K until I find that. Now I'll look at the dependence on N. I need to look at two scenarios where M is held constant but N is increased. And I see here that I increase the concentration of N by 3-fold, and that does what to the rate here? It looks like it increases it 9-fold, right? So it's 0.005 all the way up to 0.045. I'll get the calculator to verify that that's actually the rate ratio. Okay, so 4.5 times 10 to the minus 2 divided by 5 times 10 to the minus 3. All right, so the rate increased 9 times when I increased the concentration 3 times. So that means that this exponent here on N, if this doubles, and all of a sudden that goes up 3 times as much, or this didn't double, sorry, this tripled, and that goes up 9 times, or twice as much, right? And that means that this exponent here has to be a 2. All right. Now I'm in a position where I can identify what K is. I take M of any one of these 3 experiments here. I'll use the first one. The concentration of M for the first one, 0.01, and I'll use 0.01. That's the concentration of N in the first experiment up there, squared. There's going to be K value, and the rate in this scenario is 2.5 times 10 to the minus 3. All right, so I take 2.5 times 10 to the minus 3. 2.5 times 10 to the minus 3, right? And I can divide it by 0.01, and then I'll divide that again by 0.01 squared. right, which is this one over here. And then I'll be left with K, 2,500. So I can put that in here, 2,500. The units end up being for K, right? Back over here we were talking about the units. This is to the first power, this is squared, so this is m cubed. So I need to get rid of 2 m's on the bottom, and I need to have seconds on the bottom. So the units for K are 1 over molar squared seconds. All right, so per molar squared seconds. So that should be my my answer, right? The rate equals 2,500 molar squared over per molar squared seconds times m to the first and to the second. So this reaction up here is first order with respect to m and second order with respect to n. All right, that's 1460. Let's take a look, make sure we got the right answer. Yep, that looks good. And the other thing is the K value in the answer, 2.5 times 10 to the third, which is 1, 2, 3. So that's the right answer there as well. And it's per molar squared per seconds. Yeah. Okay, great. So now we move on to 462. All right, so problem 462, the reaction of iodide ion with hypochlorite ion. According to this equation, it's a rapid reaction that gives the following data. What's the rate law for the reaction? Determine the value of the rate constant with its correct units. Okay, so so our chemical reaction is provided there. The skeleton rate law, right, would be something along these lines, where we have the rate being equal to some constant times the concentration of perchlorate or chlorate ion plus hypochlorite ion plus the iodide ion times the iodide ion, and both of these are raised to some exponents of some sort. All right, and this experimental data, and that's the only way you can determine what those exponents are. You might be tempted to try to use the coefficients in front of the concentrate or the reactants, but that's not the way you can do it. You can only do it by looking at the change in rate as we change the concentration. So in this case, I can look at 2 experiments. First of all, I can look at the first 2 experiments here. In this one here, compared to the second one here, we change the concentration of hypochlorite ion. Let's see, how much do we change it? If I take the high concentration, which is 7.6 times 10 to the minus 3, and I divide that by 1.6 times 10 to the minus 3. All right, so that's 4.75. So I augmented the concentration of the hypochlorite ion 4.75 times. Let's see what it did to the rate. It took 83100 divided by the slow rate 17500. All right, so I increased the concentration 4.75 and it increased the rate 4.75 as well. So that means that the coefficient on OCl, the hypochlorite ion there, is 1. All right, let's see how the iodine concentration adjusts the reaction. So we can compare which two, the first and the third. That's where we only change the iodine concentration. All right, so let's see how much we increase the iodine concentration by taking that 9.6 times 10 to the minus 3 and dividing it by 1.6 times 10 to the minus 3. All right, so I increased the concentration 3-fold. Let's see how that affects the rate. I'm going to look at, again, 105, 105, 1, 2, 3, 4, 5, 105,000. That's my 1.5 times 10 to the fifth, divided by 17,500. So it went up sixfold as well. So I increased the rate, the concentration sixfold, and the rate goes up sixfold. So that means the concentration here, or the coefficient on the iodide ion, is also 1. So we have rate equals K, and now we can solve for K by taking the concentrations of, let's say, any of the lines. Let's say the first line. Yeah, so it doesn't indicate which one to take. When you take different lines, you might get slightly different values. So sometimes it indicates for you which one to take, but this doesn't. So we got 0.0016. We got 0.0016 here, and the rate is 1.75 times 10 to the fourth, and K's in there, and these are both raised to the 1 power. So I'm going to take 175 or 70,500, which is the rate. Solve for K here, so I'm going to divide it by 0.0016, divided by 0.0016. All right, so that's a really big number. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6.84 times 10 to the 9th. So that goes here, 6.84 times 10 to the 9th. And my units for this K value are going to be, let's see, this is molar, this has to be molar per second, right? This is molar per second for the rate. This is molar to the 1, and this is molar to the 1, so it has to get rid of a molar down here. Whoops. 1 over molar seconds. Then I'll be left with molar seconds. So this is over molar seconds. Okay? So that should be my rate law there. Alright, so that was 1462. I can double check on that one. 1462. 6.8 times 10 to the 9th is my K value, and the exponents are both 1. Alright, excellent. Alright, 1464. At a certain temperature, the following data were collected. We want to determine the rate law and the rate constant with correct units for the reaction. Alright, so here we have an example of the first reaction here. In the second reaction, we can compare those two, and we see that the difference between the first and the second reaction, we increase the concentration of the iodide, chloride, iodine, what would you call this? Monoiodine, monochlorine, chlorine. Let's see, 0.12 to 0.78. So if I take 0.78 divided by 0.12, then we increased it 6.5 times. And if I take 0.0098 divided by 0.0015, it increases 6.5 times as well. So I can see that the rate constants, the exponent on the ICL is raised to the 1. So the rate for this reaction is going to be some constant times that raised to the 1. And on the hydrogen gas, I can see that as, if I take the first and the third experiment, let's see, the third and the first, same thing, but in that direction, because we're lowering the concentration of the third experiment. So if I take the third to the first, I can take 0.12 divided by 0.089. That's an increase of 1.3 times, and 0.0015 divided by 0.0011. That's an increase of 1.3 times as well. So it looks like that's raised to the 1 power. And then I can take the first reaction there, and put in their concentrations. Whoops. 0.12 here, 0.12 here, and the rate ends up being 0.0015. So if I want to solve for my K, that's going to go right here, right? What do we got? .0015 divided by 0.12 divided by 0.12. 0.0015 divided by 0.12 divided by 0.12. So we got 0.12. So 0.12, and the units are going to be molar, molar. It's going to be 1 molar has to be gotten rid of, so we end up with molar per second. So it's molar or per molar seconds. All right. So 1464. We can double check there. Let's see. Did I go too fast? What did I make a mistake on? 1464. 0.12, 0.0015. Oh, yeah. I didn't say divide by. There we go. Divided by 0.0 or 0.12. There it is. That's our K value, 0.104. So 1.04 times 10 to the minus 1. Yeah. All right. There we go. I went too fast in my calculator. Didn't divide by the 0.12 again. All right. Excellent. So that's 1464. All right. So 1466. Data for the decomposition of this compound here, according to the equation, are given here in problem 1446, which I have below there. Show graphically that this data is first order rate law. Graphically determine the rate constant for the reaction. So here is the data, right? And what we're going to do to do it graphically, we have to open up an Excel worksheet here. So I'm going to do that now. I'm going to get a new Excel worksheet here. Okay, and I'm going to type all these numbers in. So we got 0, 1 times 10 to the 2, that's 100, and then we got 200, and then we got 300, and so forth, down to, it looks like, keep copying these down until we get to, what is it, 1100, all right, 1000, and then 1100, and then this rate here is 0.1, 0.0876, 0.0768, 0.0673, 0.0590, 0.0517, 0.0453, 0.0397, 0.0348, 0.0305, 0.0267, 0.024. All right, there we go. We have our time, right, and our rate in which the process occurs, right? So this is our time, and this is the rate. Okay. Now it says up here that this is a first order rate. So if it's first order rate, that means that for first order reaction, if I plot the concentration of a reactant versus time, right? If I plot the concentration of a reactant versus time for a first order reactant, if it's a zero order reaction, it will be a linear line. But if it's first order, it'll be like this, where you have a decay with a half-life, right? And we've also discussed that for a first order reaction, if you plot not the concentration but the natural log of the concentration versus time, this will give you a linear relationship. So I'm going to plot these really quick here. Insert a chart. This is the one I want to insert there. There it is. And it might look like it's kind of linear. I can right click on here and add a trend line and show that it's not linear, right? So I'm going to display the equation on the chart and the r squared value. And with that line there, you can see that it's not linear, and the r squared value is relatively low. Okay, so now I'm going to change all of these. Oops, this is a time. I change all of these. Let's see, is that time? Not time. It's concentration. Sorry. Oh no. This isn't. That's time. This isn't rate. This is concentration. There we go. All right. So now I'm going to change all of these concentrations to the natural log of this value there. So that's how I do that. And then I can just drag this down. There we go. And then if I just move my box over here to this one, then I get a new plot. There's my plot versus time, and I can see that the r squared value is 1. So that shows that it's a linear relationship. And also I can see that the k value, which is going to be the slope for this line, is 0.0013. Alright, so this is number 1466. I don't know if they give us an answer. Yeah, they do give us an answer, and they say 1.32 times 10 to the minus 3, which is our value that we get there. Alright, excellent. So that's how you plot graphically and get your rate constant for a reaction. Alright, so number 1468 now. We have the same chemical reaction as we've been talking about previously, decomposition of thionyl chloride, and we know it's we've been told it's a first order reaction, and they say that there's a first order rate constant of that 2.2 times 10 to the minus 5 at 320 Celsius. If the initial concentration in the container is 0.004, what will its concentration be after 1 hour? All right. So this is a first order reaction, and so we want to know the concentrations versus time. And we know that if we take the natural log of the concentration initial, concentration of the reactant initial over the concentration at some time, then that will equal KT. Now this equation here, you can see it on page 685 of the text. It comes from the idea that for a zero order reaction, well, just if we deconvolute, well, we don't need to deconvolute it. You should go through that and deconvolute it yourself. We did it in class at one point as well, but and this is an equation that would generally be provided for you on an exam. So, but what we can do with it is we can use the K value, 2.2 times 10 to the minus 5. The time value, now that's in per seconds, 2.2 times 10 to the minus 5 per second. So time has to be in seconds as well. So if we do 1 hour, that has to be 60 seconds. So that's to solve the question for, this is per second. That's to solve the question for A, letter A here, right? And the resulting initial concentration was 0.004, and we want to know what the new concentration will be. So we can break this down by saying the natural log of initial concentration 0.004 minus the natural log of, this will be the final concentration. Okay, so when you have natural log of a ratio like that, you can break it down like this. Okay, so we get our calculator, 2.2 times 10, 2.2 times 10 to the minus 5, all right, times 60. Okay, so we got a value there, and then we're going to Also take the natural log of 0.004. Alright, so we got that value there. And we're going to bring the natural log of 0.004 over by subtracting it from both sides. So if we take this value here, which was the product of these two, right, and subtract this, the natural log of 0.004, and we get that value, and that's going to be equal to what's left over here, which is going to be the negative natural log of x. So if we divide that by -1, makes it just the natural log of x will now be equal to this value. So if I raise e to that value, it's going to tell me that x equals 0.00399. And that's the concentration after the 60 seconds. Alright, so I can double check that one. 1468. 3.7 times 10 to the minus 3. 1, 2, 3. Did I make a mistake here? What did I do wrong? I took natural log of 0.004. That's that value there. I took up here 2.2 times 10 to the minus 5 times 60 seconds. 0.0132. Alright, so if we solve the second one in 1468, same equation here. Same equation, 1468. The initial concentration, 0.004. The natural log of 0.004 over x is going to be equal to k, which is 2.2 times 10 to the minus 5 times 1 day. That's 24 hours. And we're looking for minutes, or let's see. Oh, maybe that's what the problem was. Maybe last time I didn't take into account sort of an hour in hours. 24 times 60, that's minutes, times 60, that's seconds. So 5184000 times 2.2 times 10 to the minus 5. Alright, and this is going to break down natural log of 0.004 minus natural log of x equals 2.35 times 10 to the 11. Alright, so I'm going to take the natural log of 0.004. I'm going to take this value up here and subtract that value. So then I have that value, which is I'm going to make negative by moving this sign over, and then that is not right. So what happened there? What did I do wrong? So this is after 1 day. Oh, 1 day? How'd I get 1 day is 24 hours. Okay, try that again. 24 times 60 times 60. There we go. 86,400, not that value. Times 2.2 times 10 to the minus 5. Alright, 1.9. Subtract the natural log of 0.004 times a -1 to move that negative sign over, and then the natural log of that value is 5.9 times 10 to the minus 4, which is what we got in the back of the book. All right. Very good.